In the last lesson, we noticed that linear approximations could provide a relatively good estimate of what a function was doing in a particular location, as long as we were using a particular thing. What we are going to do now is around that particular point is we're going to look at the difference between what the linearization is doing and what the actual function is doing, and then use these. We're going to call each of these differences. So we have our difference, and particularly the difference in the y values for the tangent line and the y values for the function, and use these to calculate things. So these are called differentials. So if we have y equals f of x, we call x the independent variable, and y is the dependent variable. So what we are going to do is we are going to consider dx to be an independent variable. And we are going to define dy by the idea that we have dy over dx equals f prime of x. So we're going to define dy as a dependent variable, and it's dependent on x, and we are going to say that dy equals f prime of x times dx. So we're going to think of it as a little tiny bit of a function. Okay, so let's actually define these a bit more geometrically, because it can be a bit easier to understand here what we are talking about. So if we have a function and we have a line that is tangent to the function at a point, we think of when we're thinking of going to another point on the function, we look here at this next x value. So we take a point, this is our x, our original x, and this is our right here coming down. We consider this to be our delta x, our change in x. So delta x is the amount that we're changing on the function, and that is the same as the amount we're changing on the tangent line. Okay, so we're going to take dx and dy. So dy is f prime of x times dx, so it's going to be the difference between right here, it's going to be this whole length here. So this is our dy, whereas this right here between our x value here is going to be our delta y. Okay, so we're defining delta x and delta y just to be the change in x and the change in y as we move from an x value to another close point on the function. And we're defining dy to be the change in the tangent line in the y, and dx to be the change in the tangent line in x. And delta x and dx are the same. So we say delta x equals dx. And as delta x gets smaller, dy approaches delta y. So we're thinking of delta x and delta y as the actual values of the function as we move away from this point, whereas dy is the value of the tangent line. So the bigger the difference between dy and delta y, the less well our tangent line is approximating our function. The smaller the difference between dy and delta y, the better the tangent line is approximating our function. So let's look at the difference between how well our function is approximated by looking at the values of dy and delta y for, we have y equals 3x squared plus 1. So delta y, so let's, for example, 1, okay, compare. So this is almost a process of evaluating how good of an approximation our linearization is at particular points, depending on how far out you're going from that point you're doing the linearization around. So for example 1, we're going to compare the values of dy and delta y if y equals 3x squared plus 1, and x changes. Okay, so a is from 1 to 1.2. So if we're going to try to look at how effective is a linearization that's done around 1 compared to what's happening at 1.2. Okay, so delta y is y evaluated at 1.2 minus y evaluated at 1. So it's just the difference in the values of the function. So we're going to actually plug 1.2 into our function. So we have 3 times 1.2 squared plus 1. And we're going to subtract 3 times 1 squared plus 1. And we get 1.32. So that's the actual difference in the y values for the function. Let's look at what's happening at dy. So dy is f prime of x times dx. So this is equal to 6x times 0.2. So dx is 0.2. We're changing from 1 to 1.2. That's how far we're going. Our x is 1 that we're doing this linearization around, times 0.2, which gives us 1.2. So our tangent line approximation of how far this is going is 1.2. Our actual where this is going is 1.32. So it's accurate, but not that super accurate. However, if we're going to look at let's look at 2 points that are closer together. So you can see we're only 0.2 apart, and already our linearization is starting to break down. It's accurate not even to 1 decimal place. So it's accurate to the whole number, but not to the decimal place. Let's see what happens when we look from 1 to 1.01. Okay, so delta y equals y at 1.01 minus y at 1. So we're just going to evaluate it there, which is 3 times 1.01 squared plus 1 minus 3 times 1 squared plus 1. That's some lovely big calculations, which is 0.0603. Now let's try dy here. So dy is f prime of x dx, which is 6x times dx. Here we're only changing by 0.01. So this is 6 times 1 times 0.01. That's our dx, which is the same as our delta x, the change from the point we're evaluating around to the point we're looking at. And that is 0.06. So that is much more accurate. That's accurate to 2 decimal places. It's actually accurate to 3 decimal places. So what you can see is the closer we are, and what this whole differential thing allows us to do is evaluate how accurate our linearization is going to be for the point that we're looking at. What's the actual difference? Okay, so and just to sum it all up, as dx decreases, the error in approximating delta y with dy decreases. Okay, so let's look at another way in which this could be useful. So example number 2. Use differentials to find an approximate value for the cube root of 65. So notice cube root of 65 is close to an actual perfect cube. So this might be somewhat more effective than we would think. So let's define a function. So let's let y equal the third root of x, which is x to the 1/3 power. Okay. So we notice that x equals 64. We're going to look at what happens as we go from x equals 64, and we're going to use our approximation at x equals 64 to try to estimate what's happening at x equals 65. Okay, so we know we know f of 64 equals 4, because the cube root of 64 is 4. So dy is equal to f prime of x times dx. So it's equal to 1/3 x to the negative 2/3 times dx, which equals 1/3 times 1 over the cube root of 64 squared. And I'm going to actually square after, not before, because that's just going to be an easier computation, times 1. Cube root of 64 is 4. 4 squared is 16. Okay, and dx is 1 because we're moving over 1. So we have 3 times 16, which is 1 over 48. So the cube root of 65 is approximately equal to 4 plus 148. And you might notice this is really the equation for our linearization. So f of a plus f prime of a, x minus a. So differentials and linearizations are really, really, really closely linked. Okay, and you can often, things you can do with one, you could do with the other. So notice that we have, this is equal to, our estimate is approximately 4.0208. The actual number here is 4.0207. So it is really, 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 really close. Okay, last example. So since differentials are really tied up with how much error there is in our linearizations, we can use them to calculate error. Okay? So we're going to assume we're going to use our differential to represent an error calculation. So the radius of a sphere is measured as 21 centimeters with a possible error of at most 0.05 cm. What is the maximum error in computing the volume of the sphere using the measured value of r? Okay, so that's the possible error in our radius. Okay, so we're going to look at the corresponding dv, the error that we're going to come up with in volume. So error in r equals dr. So we're going to let that equal dr. So that's 21 centimeters, and that's 0.05 centimeters. The error in the value is then going to be dv. So we can relate dv to dr by using the derivative. So we have v equals 4/3 pi r cubed. dv equals 4 pi r squared times dr. Okay, we're just looking at our error. So dv is 4 pi times 21 squared times 0.05, which is 277 centimeters cubed. This is our absolute error. So that's the amount of error. Sometimes it can then be more accurate to look at what this is compared to what we're actually talking about in terms of the volume. So our actual volume is 4/3 pi r cubed, which is 4/3 times pi times 21 cubed, which is 38,792 centimeters cubed. So 277 may have seemed like a fairly large number, but when we compare it to the actual volume, it's not as gigantic. So we can look for the relative error by taking dv over v, which is 277 over 38,792 times 100%, which gives you 0.71. So it's a less than 1% error, so that actually makes it feel just a wee bit more accurate.